Hi, thanks for joining me. Today I'm going to be sharing with you what I believe is probably the most useless theorem there is. There might be other useless maths theorems out there, but I think this is the most useless. Let me describe what it is, and then I'll state what the theorem is, and then get into a proof. Okay, so let's just observe that 1 factorial over e is 0.3678 something, 2 factorial over e is 0.73 something, 3 factorial over e is 2.2 something, 4 factorial over e is 8.8 something. Now these might not seem particularly interesting, but if we just focus on the integer part, so the floor of each of these numbers, so basically we just ignore what's after the decimal point, we get 0, 0, 2, 8. Now all of those numbers are even. Now that's what the theorem is. I claim that this pattern continues. So n factorial over e is always even. Let's get stuck into a proof. Okay, so before I get stuck into the proof, just this notation here, the things that look like right angles, that just means the floor. So this thing here is the greatest integer smaller than or equal to n factorial over e, and we claim that that's even for every positive integer n. Now, we've got to introduce a definition of e, and the one I'm going to be using is the power series definition, which says that e to the z is the sum of z to the k over k factorial from k equals 0 to infinity. So if we notice that n factorial over e is just n factorial times e to the power of minus 1, and e to the power of minus 1, then we can use our power series definition. So n factorial over e is just the sum from k equals 0 to infinity of minus 1 to the power of k over k factorial, and then of course we've got to multiply through by this n factorial, so let's just put that there. Okay, and now what we're going to do is just split this summation into two different summations. So we're going to sum from k equals 0 to n, and then from k equals n plus 1 onwards. So this is a sum from k equals 0 to n of n factorial times minus 1 to the k all over k factorial, plus the sum from k equals n plus 1 now to infinity, so write that as k being greater than or equal to n plus 1, of the exact same thing. Like so. Okay, now I claim that this guy here is either minus 1 plus a little bit or just a little bit, depending on whether n is odd or even. But basically, what we're going to do is, because we're considering the floor of this expression, what I claim is, because obviously this guy here is an integer. Why is this obviously an integer? Well, if we look at from k equals 0 to n, k factorial is a factor of n factorial because k is less than or equal to n, and n factorial is just k factorial times the integers bigger than k but less than or equal to n. So this guy here is always going to be an integer, and we're just timesing by minus 1, alternating. This guy is going to be an integer, and I claim that this is either a small bit, like between 0 and 1, or it's between minus 1 and 0, depending on whether n is odd or even. So let's examine this, and then once we know what this guy equals, we can write the floor of this guy here is just this thing, and then maybe with a minus 1 here. Anyway, let's have a look at this guy here. Okay, so the first thing I want to do is show that this guy here has magnitude strictly less than 1, and that will tell us that it lies between minus 1 and 1, and then I'll check to see whether it's positive or negative depending on whether n is odd or even. Okay, so let's firstly show that this has magnitude less than 1. So the magnitude of this guy here, and then just using the triangle inequality, this guy here is less than or equal to, when I bring the magnitudes inside the summation, of magnitude of minus 1 to the power of k times n factorial over k factorial. Of course, n factorial and k factorial are positive. The only thing this magnitude thing works on is the minus 1 to the k, so that just gets that to disappear. So this is just the sum from k equals n plus 1 to infinity of n factorial over k factorial. But now notice that we've got n factorial over k factorial, and k factorial, k is going from n plus 1 onwards, but in particular, the bottom thing here, if we just perhaps write out the first few terms, we'll get n factorial over n plus 1 factorial, plus n factorial over n plus 2 factorial. Let me write one more term out, n factorial over n plus 3 factorial. Okay, but of course we can do some cancellations from this guy. This is just 1 over n plus 1. This is just 1 over n plus 1 times n plus 2. This is just 1 over n plus 1 times n plus 2 times n plus 3, and so on. Now, because n is a positive integer, we know that 1 over n plus 1 is going to be less than or equal to a half. And because, so then that means that 1 over n plus 1 times 1 over n plus 2 is going to be strictly less than a quarter. This guy here is going to be strictly less than an eighth. The next term is going to be strictly less than a 16th. So this guy here is going to be strictly less than a half, plus a quarter, plus an eighth, and so on. And this guy is just 1. Okay, so we've shown that the magnitude of this guy here is strictly less than 1. Now let's show whether it's positive or negative depending on whether n is odd or even. Okay, so we just showed that this guy here has magnitude strictly less than 1, so that tells us it's between -1 and 1. Now I've just written out the first two terms of this sequence here, and now what we're going to do is examine the behaviour when n is even, and so what is the behaviour when n is even? So if we look at this guy here, when n is even, the first term here is -1 to the power of even plus 1. So even plus 1, of course, is an odd. So we get -1 to the odd, so this guy here is just -1. So then, if n even, this guy here is equal to -1 over n plus 1, then plus 1 over n plus 1, n plus 2, because of course, if n is even, then n plus 2 is even, and -1 to the even is 1. Okay, and the next term will be -1 over n plus 1, n plus 2, n plus 3, and the fourth term, n plus 1, all the way up to n plus 4, and this continues. So we're getting minus, plus, minus, plus, minus, plus, but notice that the magnitude of this guy here is 1 over n plus 1, and the magnitude of this guy here is 1 over n plus 1 times 1 over n plus 2. So the magnitude of this guy is strictly less than the magnitude of this guy. But because we're looking at the negative of this, when I add these two terms together, I'm going to get a negative number. Similarly, when I add these two terms together, I'm going to get a negative number. When I add the next two terms, a negative number. The next two terms, a negative number, and so on. So I'm just adding up a bunch of negative numbers, so of course the solution is going to be a negative number. And because we know it's between -1 and +1, and we now know it's negative, that means we can write this thing here. If I call this expression Sn, for n even, Sn, oopsie daisy, is equal to -1 plus some epsilon n term. So this is just some small number between, a small positive number between 0 and 1. And that's essentially what I mean by Sn is -1 plus epsilon n, because it's between -1 and 0. Okay, and that's for n even, and then for n odd, I'll leave it as an exercise for you. It's not too difficult. Use a similar argument, except essentially these minus signs and plus signs are the other way around. You get that Sn is just epsilon tilde n, say. So not the same epsilon n, but again, it's just some small number, small positive number, so it's between 0 and 1. Okay, so now this proves that what I said about Sn being between either -1 plus a little bit or just a positive little bit. Now what we're going to do is go back to looking at the floor function of n factorial over e. Okay, so let's just quickly go over what we've proved so far. We've shown that n factorial over e is equal to the sum from k equals 0 to n of -1 to the power of k times n factorial over k factorial, plus this Sn term, which is kind of like an error term if you want. And Sn is either -1 plus epsilon over epsilon n, where n is even, or it's epsilon tilde n, where n is odd. And epsilon tilde n are just some small positive numbers between 0 and 1. So not including 0, not including 1. But yeah, something like that. Now what we want to do is look at the case n equals even for this guy here. So if n is even, now we want to actually consider the floor of n factorial over e. Well, we know that n factorial over e is going to be this guy here, which we know is an integer, -1 from this Sn term, and then plus a small positive integer epsilon n. So if I just write this out explicitly, this is just -1 plus the sum from k equals 0 to n of -1 to the k times n factorial over k over k factorial, sorry, plus epsilon n, like so. So I've just brought the -1 onto this bit here and the epsilon n there. Okay, but of course this guy here is a small, between 0 and 1. This guy here is an integer, so this thing here is just -1 plus the sum from k equals 0 to n of -1 to the k times n factorial over k factorial, like so. Now, we look at this thing here and ask ourselves, when is this guy here odd? Because most of the terms in this sort of summation here are going to be even. Well, why is that the case? Well, if k is less than or equal to n plus 1, then this guy here is always going to have an n on the numerator, and thus, because n is even in this case, we're always going to have something even in the numerator. So that means that we're just adding up a bunch of even terms. The only time that doesn't apply is when k equals n, in which case we have minus 1 to the power of n, and minus 1 to the power of n is just 1 because n is even, times n factorial over n factorial, which is just 1. And then you can see that that 1 is going to cancel nicely with that minus 1. So all we're left with is essentially the sum from k equals 0 now to n minus 1 of minus 1 to the k times n factorial all over k factorial. And now, because we're only summing from k equals 0 to n minus 1, each of the terms here are even. We're adding up a bunch of even numbers, so the result is going to be even. So that shows that the floor of n factorial over e is even when n is even. Now let's quickly look at when n is odd. Okay, so now we look at the case n is odd, and what I'm going to do is write this summation here, but actually just take off the last two terms. So we've got n factorial over e, and the floor of that is going to be the floor of the sum from k equals 0 to n of minus 1 to the k times n factorial over k factorial, plus this epsilon tilde n, because now we're looking at n being odd. But again, this guy here is just some number between 0 and 1, so when I take the floor of this guy, that thing vanishes, and I've just got the sum from k equals 0 to n of this guy here. But as I said, I'm going to look at the sum up to n minus 2 and then take off the last two terms. Okay, so this is minus 1 to the k times n factorial over k factorial. And then I'm just going to look at the k equals n minus 1 and k equals n terms separately. So when I plug in k equals n minus 1 to this, I'll get minus 1 to the n minus 1. But remember, n is odd, so n minus 1 is even. So n minus 1 to the n minus 1 is minus 1 to the even, so that's 1. So we get plus n factorial over n minus 1 factorial, which is just n. And then when I plug in k equals n, I get minus 1 to the n, and n is odd, so minus 1 to the odd, which is minus 1. Then n factorial over n factorial, so that's just minus 1. And then I've got this guy here, but I claim that this guy here is even, or it's at least a sum of even terms, so in particular it is even itself. Why is that the case? Well, it's similar to the argument before, because if I look at this thing here, because k is only going up to n minus 2, on the numerator here I'm always going to have an n and an n minus 1, and because n is odd, n minus 1 is even, so I've always got an even number sort of in the numerator multiplying out, so I'm just multiplying something by an even number. So this guy here is always going to be even, so when I sum up a bunch of even numbers, I'm going to get an even number as well. So this thing's even, but remember n is odd, so n minus 1 is even, so we've got even plus even, and that of course is even. So that proves that the floor of n factorial over e is also even when n is odd. And that concludes the proof. We've proved that the floor of n factorial over e is always going to be even. And as I said at the start, this is the most useless theorem I think I've ever heard. I don't know. I can't think of anything more useless. There are probably more useless theorems out there in maths, but I thought it was pretty cool, something that's kind of interesting and certainly not intuitive. You wouldn't expect for the floor of n factorial over e to always be even, but it turns out that it is. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.